Dear colleagues, it's now 5 p.m. in Tomsk, and I'm happy to start our next talk. I'm happy to introduce our today's speaker, Igor Nikonov from the Moscow State University will tell us about crossing tribes of tangles in a thickened surface. Let's welcome.
Thank you. My talk is devoted to description of labeling on of tangle diagrams in thickened surface, and I work in the combinatorial approach to knot theory, where we consider knots and links as diagrams, that is covariant graphs with structure of overcrossing and undercrossings, model some transformation or Reidemeister moves. And we on crossings and consider the following problem. We try to find some labeling of crossings which would be compatible in some sense with the Reidemeister moves. We can distinguish different crossings, for example, crossings, loop crossings from other crossings. We can construct invariants and solve some other problems concerning knot classification. The simplest example of when this approach works is linking invariant. If we have two component link, then we can distinguish self-crossings from mixed crossings where two components intersect. And if we can take all mixed crossings and take the sum of their signs, plus or minus, then we get the known linking numbers. Number of this link, this is one of the first link invariant. So we can apply this approach in many different situations. For example, if we consider a virtual node diagram, we can take any crossing and take half of the diagram at this crossing and count the number of classical crossings on the half and take the parity of this number. We get some number 0, 1, which is the Gaussian parity of the crossing. And again, if we take the sum of the signs of odd crossings with the 1, we get odd right number of the invariant introduced by Louis Kaufman in 2000. About this time, Vladimir Turaev introduced another knot invariant. He worked with flat nodes, that is virtual nodes, where we don't distinguish between overcrossing and undercrossing. And again, we can take some crossing and take the right half of the diagram at the crossing, and then take the intersection number of this right half and the cycle presented that presents the diagram. We get some integer number, some index n of v, and if we take the sum of the signs of this index multiplied by formal variable t power the model of this n, for all crossings where this number is not 0, we get a polynomial invariant. And this is the first example of so-called index polynomial, it becomes one of the main invariant, one of the widely used invariant for virtual nodes. We try to consider not flat nodes but virtual nodes. We can use the signs of the crossings, and if we modify some this number n by this node crossing, we get the known number index of the crossing, and the conventional index polynomial is just the sum of signs of the crossing multiplied by the formal variable power index. And this index polynomial in various forms appeared in works of many authors, and Turaev also considered some kind of this invariant for nodes, more precise, for nodes in the surfaces up to co-bodies. That means we also consider this. That means we consider virtual nodes up to co-bodies. Turaev proved that this polynomial is concordance invariant. So we can try to generalize this kind of invariant and consider some other indices. And the problem is what property we can get from these indices to define this invariant. And the property of index was formalized by Chen. He proposed that a chord index should possess the following properties. First of all, if we have some crossing, and then Reidemeister move shouldn't change the index value of this crossing. And if we have second Reidemeister move, then two crossings which take part in the move should have the same index. And for the first Reidemeister move, we can require that the index value of these crossings should be some fixed value. In fact, we can take a few number of axioms. For example, we can omit the first conviction and get what is called weak chord index considered by Su. And using this index, we can define some polynomial invariant. There are many examples of indices in literature. Some of them are numbers, some of them are matrices or homology classes, some of them are diagrams. And all these indices have a drawback because they are all trivial for classical nodes. And the question is to find some index which would be non-trivial for classical. And my work answer this question. We consider nodes and links in two-dimensional surface, and we take not nodes, but we allow to consider non-closed components, so that we consider tangles in a thickened surface. Tangles may include closed components or long components, that is components of boundary. And projection of this tangle on the surface will give us diagrams on surface. So we formalize the definition of index and consider the diagrams of a fixed tangle as a category where objects are diagrams and morphism are composition of elementary morphism, that is isotopies, Reidemeister moves, and matrices we consider tangles in surface up to homomorphism of surface. And then the correspondence between diagram and the set of its crossings is a function from this diagram category to category of finite sets and partial bijections between. Then we can define index as a family of maps which map each diagram to some fixed steps, and we require that this map should obey these two properties. The first property is that any elementary morphism, that is isotopy or Reidemeister move, should keep the value of index. So if we have some crossing and apply Reidemeister move and have the corresponding crossing new diagram, the value of indices should be the same. And the second requirement is that in the second Reidemeister move, the index values for the crossing that take part in this move should coincide. It is useful also to define so-called signed index, where we map our crossing to some a set with an involution, and we can replace the second condition with the following one. We require that the values, index values for the crossing move should differ by the involution. For example, if we take the sign function, the sign of the crossing, it is an example of this sentence. There is some correspondences between indices and signed indices. If we have the sign function on the crossing, then we can transform each signed index to a usual index by this simple formula. And vice versa, if we have an index, we can define a signed index by adding the sign function to the index side. So there is also a bijection between indices and signed indices. If we have a first Reidemeister move, then there are 4 types of loops which appear, and this loop corresponds to 4 possible values of index on the crossing that move. And well, we can prove that if we consider, for example, index, the value of these 2 type loops and these 2 type loops coincide. And if we work with a signed index, that these values differ by the involution. So we have 2 involution values, which correspond to loops. And using this, we can define a general definition of index polynomial, or I call it linking invariant because it generalizes the linking number. So assume we have a signed index, then we have a set of some values which correspond to loops. We exclude these values and take the free model generated by the rest values and factorize by this relation. And then just the sum of signed indexes for all crossings which differ from the loop give us some invariant. Some invariant in this free model. And if we have not a signed index but index, then we can define some invariant by this formula using the sign function of the crossing. And the signed index allows us to define index polynomial-like invariance for flat nodes. Okay. So if we want to define some invariant like this for classical nodes, we should find some index. Among all indices, there is the universal index, which produce all other indices by some map of coefficients. If we map coefficients to other coefficients, that we get a new index, which is just composition. If we want to find nontrivial indices for example, classical nodes, it is enough to consider only universal index. And my result is a description of the universal index for tangles in a fixed surface. And I make one further step for generalization. Consider not indices, but the partitions of crossings into subsets which are induced by an index. If we have an index, we can split the set of crossings into subsets where the value of index is the same. So we can, from the beginning, consider the splitting. That is, we split the set of indices into subsets. We require 2 conditions which correspond to conditions of the index. That is, if 2 if two crossings belong to one subset, I call this subset tribes. Then after application Reidemeister move, the corresponding vertices also should belong to the same tribe. And the second condition is that when we take a second Reidemeister move, then the two crossings of this move should belong to one tribe. And this condition take the equivalence relation on the set of crossings for all diagrams generated by these two conditions. We get a set of these subsets in a set of crossings, and I call this the finest tribal system. And from definition, it follows that if we have two crossings and they belong to one tribe, then for all indices, the value of index on these two crossings will be this. And what is the difference between tribes and crossings can be explained as follows. For example, take a diagram which has a symmetry. For example, this trefoil diagram, we have three crossings, 1, 2, 3, and if we consider any index, the value of this index should be the same on all the crossings due to symmetry. On the other hand, theoretically, it may be that these three crossings define three different tribes. And when we apply the symmetry that is rotate the diagram, this symmetry induces permutation on the tribes. Well, the tribes may be different, but any index will be the same on all the crosses. So tribes maybe give us some finer description of the cross. So let us pass to out the description of tribes for tangles in a fixed. Let us consider the following indices. Assume we have a tangle with n components. Then any crossings can be described by the number of components which intersect at this crossing. Thus, we have the component index. That is these two indices of the component. If we have a self-crossing of a long component, then we can define and distinguish between early or undercrossing, early overcrossing. When we move from the beginning of the component, we pass first undercrossing, then overcrossing, or other situation when we pass over and then under. And this gives us order index with the values in Z2. And the third ingredient is the homotopy type. If we have a crossing, then we can take a half of this crossing. For the one component, we move from the first point of the component to the crossing and then move along the half and return back. If we have a closed component and the self-crossing, we take a base point on this component, move to the crossing, and then move from the undercrossing to the other crossing, back to the crossing, and return to the base point. And if we have a mixed crossing, then we move from the base point on one component to the overcrossing, then from the undercrossing to the base point of the other component. In all cases, we get a path, and we consider the homotopy class of this path. And this will be an element of some homotopy group. And after we factorize this element by joint action of the homotopy class of the component, or by action of the component from left and right in the mixed case, so we get graph pi bar. We get homotopy class in this graph, and this will be a homotopy type of the crossing. Note that this homotopy is this type is not an index because it depends on the diagram. We must choose some base on the diagram. And the central result is the following. Assume we have an oriented tangle with numbered components on the surface, and take some diagram and some two crossing on this diagram. Then these two crossing belong to one tribe. If and only if they have identical component index, order index, if crossings are self-crossings of the long component, and homotopy type. These three indices types describe the tribe. And as a cohort, we get the following result. Assume we have a classical node. Then we have one component, so there is no component index. Node is closed, so we have no order index because order index is for long components. And finally, classical nodes are nodes in a sphere, and sphere is simple connected, so there is no homotopy type. Homotopy type is trivial. That means that all crossings in any component of a classical, in any diagram of classical node belong to one tribe. And that means that the values of any index of these crossings is the same. That is, any index on classical nodes is trivial. And if we consider not nodes but classical links, we get a component index. We don't have order index, and homotopy is trivial type. So the component index is universal. It's the only information we can get for crossings for classical links. And another consequence is that if we work within the full torus or thickened annals, node here, then the homotopy group of this annals is Z, so we have the homotopy type is described by this integer value. So now we can distinguish our crossings by this homotopy class of half of diagram half at the cross. So we have is V is the universal index for nodes full torus. Okay, so I have minutes, and I guess keep some slides. So we can apply this result to virtual links. Virtual links are nodes in surfaces up to isotopy and stabilization. So if we have the result of Kuperberg that claims that we can take the surface of minimal genus, and any representatives must be homeomorphic. And then this homeomorphism of the surface generates some action on homotopy group of the surface. And if we have some tangle, we have some symmetries, diffeomorphism that maps this tangle to itself, and this gives us some subgroups in the automorphism groups of the surface. If we factorize the homotopy group by this surface, by the symmetry subgroups, we get homotopy index, and this homotopy index is a well-defined index for all terms of fixed virtual link. This homotopy index with the component index give us the universal index of virtual diagrams of some virtual links of minimal. And I maybe finish with an example. Consider first that is square with identified opposite sides, and this two-component link. You can see that there is a symmetry which rotate this torus by pi, and this symmetry induce the map x to minus x in the fundamental group of the torus. So the homotopy index would be z2 by this involution, and here we have 8 crossings, and they give us 4 values of universal index, because if we, for example, consider vertices with the same component type, for example, these two self-intersection of this component, and then if we arrange this component like this, the below crossing gives us as a homotopy index this curve, and the upper crossing gives us this the homotopy class of this curve, and these curves are different because they have opposite direction, but when we apply this involution, this symmetry, they will be the same. So in this picture, we have any two crossings with the same component type have the same homotopy type, so we cannot distinguish them by index. So I finish here. Thank you for your attention.
Okay, thank you, Igor, very much for your interesting talk. Are there any questions or comments? Remarks, maybe? Well, it would be very nice to elaborate similar index theory, not for just crossings, but for some other things, maybe for crossings of two knots, or maybe for triseconds, or maybe for whatever objects which appear discretely in generalizations of knot diagrams, not just Reidemeister knot diagrams. It would be very nice. Okay, are there any questions or comments? Let's thank the speaker again.